Окей. So let's start. Да, правильно ли я понимаю, что я нужно на английском?
Ну да.
Да. Okay. Then in English. Okay. Is the question, is anybody trying to watch the recording of the first lecture? Because I'm not sure that it's a strange format of this Yandex Telemost, so I don't know, in fact, is it work or not. So if anybody yet tried or will try, please say something that all is okay or...
Смотрел запись, которую ссылку выкладывали в группе? Не пробовал смотреть? Ладно.
Okay, doesn't matter. I hope that it will appear at Madfuck YouTube channel in a couple of days. Okay. Nevertheless, so on the first lecture we gave some very overviewing introduction of topological recursion, and today we'll try to compute something. So we decided to just start with this huge formula of topological recursion relation, and we will try to compute something. So maybe you see, if you are or you were a participant of a seminar of Kozaran Landau, maybe you saw the formula of topological recursion, but nevertheless, it is quite huge, and I will try to explain the details of this formula today, and during the practice we will compute something. Okay, so topological recursion. The recursive. Okay, let's the formula. We, as we said, we have some initial data which calls spectral curve. Doesn't so it doesn't connect straightforward to spectral curves from mathematical physics, but it calls spectral curve. So initial data of the recursion spectral curve. Spectral curve. What is it? It's four tuples, so four guys in this spectral curve. It's sigma is a Riemann surface. Sigma Riemann surface X, and so we always have some local coordinates on our Riemann surface, and we usually will denote this coordinate. I will usually denote this coordinate by z. So z is my local coordinate on this Riemann surface. So I have two functions, x of z and y of z. So z is a affine coordinate on sigma, and some meromorphic functions. And which it usually calls b. It's a b differential on the square of sigma, so it's a b of z1. Yes, and we have sigma, and we we will have some Cartesian products of this sigma. So we will have many copies of the sigma. I will denote it by sigma squared, etc. Sigma to the power n. So it's a Cartesian product of sigma. So it's a sigma times sigma, some copies of sigma, and z small with indices are coordinates on these copies of sigma. So if I'm writing b of z1 z2 means that z1 is a coordinate on first copy of the first copy of sigma, and z2 is a coordinate on the second copy of sigma. So this guy, so it lives in sorry, sigma squared, and it is dz1 dz2 over z1 minus z2 squared. So it's a two form which lives on the sigma times sigma. Okay, so z1 is a coordinate on the first copy of our Riemann surface, and z2 the coordinate on the second copy of sigma. So and this for tuple called spectral curve. So spectral curve is a sigma x, y, and b.
Yeah, sorry. So there is a misprint. So B does not belong to sigma squared. It lives on it.
Yeah. Sorry. Yeah.
Z1, Z2 belongs.
Yeah. So yes.
Is the local or global coordinate? And what about B? Is the local or global?
So this B as written here is for the case of when sigma is a ring sphere.
Yes.
Then B is a global coordinate on the ring sphere, and of course, if you have some surface of higher genus, then you cannot have.
Yes. What I should. Yes, I more or less could hear the questions, but yeah, thanks for answering, Petya. So yeah. In fact, what I wrote. So in fact, this B, the proper definition of this B is a bit harder, but this form of B always. So we always can choose B in such a form if sigma is equal to CP1. So maybe let's for the beginning, maybe for the half part of this course, we'll agree that sigma will be just a CP1. Yes, I should so remark. So you can choose B as if sigma is CP1. If
So, can I make my one small remark? So you have this in the general case when you have some higher genus, then we have some requirements on B. It doesn't have this form as written here, but it is still required to have a double pole on the diagonal. So on the you see here in this CP1 case, when Z1 is equal to Z2, you have like a pole of order 2 on this diagonal in this Cartesian square of sigma.
so maybe let me write it down. Yes. So in general case, in okay, in case genus sigma greater than 0, then we have conditions on B. We have the following conditions on B. So yes, as Peter said, that it should have double pole on the diagonal. Say and also the second condition that so the intersection of B with the set of A cycles on this Riemann surface sigma should be 0. Yes, so I don't want to say more about much more about this second condition, but if you know something about topology of Riemann surfaces, so say integral of B over some A cycles is equal to 0. But nevertheless, in case of
in most applications, we'll deal with genus 0 spectral curve. So for now, just forget about this.
Yeah.
Related to higher genus. So
In-
let's see that we are in the genus 0 situation.
In all our computations, I think, if we will be too smart to go to the genus 1, it will be great, but I think we will stay in genus 0. Okay, so we have this 4 guys, sigma x, y, and b, which is equal to dz1, dz2 over z1 minus z2 squared. Yes, some questions? Any questions? Okay. And
Здесь вопросы?
да, может, надо что-то повторить по-русски. Есть такая традиция на некоторых семинарах. Okay, and we have a couple of conditions on these functions x and y. So okay. For example, yes, sigma cp1 x of z is equal to d squared over 2, y of z is equal to z, b as usual, dz1, dz2 over z1 minus z2 squared. So, for example, here we take some more or less the easiest two functions, x and y. So we could take, for example, as x and y this function, or we'll see a lot of other examples. Okay, so what conditions on x and y? Conditions on x and y. First, that critical. So, I think in the whole course, again, the critical points we want the critical points of the function dx over x will be simple. So critical points of let's say zeros, if I write in this way, zeros of dx of z over x of z are simple. And the second condition, that zeros of dy are away from zeros of dx over x. So, for example, here in this example, x is equal to z square over 2, we have dx is equal to just okay, this is a bad example for this. Okay, in this notation it should be a bit.
Maybe you don't have to divide by x, just dx.
Yes, but for simple Goretz number, for my notations for simple Goretz numbers, I should divide by x. Okay, let me. The problem is, let me a bit change this example. Let me write here z e to the power minus z, and this is our running example for today. Why am I confused? Because of this, the result, we have some freedom of choosing this, what exactly we use as say initial data for the recursion, and therefore in different notations we we use different x and y for different particular problems, but nevertheless let's say this way. So we have that I want that the zeros of dx over x are simple and zeros of dy are away from zeros of dx over x. And in this example I have, so dx over x is equal to, I think, what it will be. So example, it will be, say, something like this, yes, minus, so it will be 1 minus z e to the power minus z over z e to the power minus z dz, yes. And this is dx over x in z coordinate, and I have 1 minus z over z dz, and this guy has zero at simple zero at z is equals to 1, so z is equal to 1 simple 0 of dx over x, and dy, y we have just z, so no zeros of dy, so the second condition always also holds. Okay, and this is what we had. We have a spectral curve, and we have some conditions on the spectral curve. This, and from the spectral curve, we obtain the initial data of the recursion. Initial data of the. I'm sorry for this. Some reconstructions around of the recursion. Are omega 0 1 of z and omega 0 2 of z1 z2. Omega 0 1 in my notation today, it is just y. It's the form y dx of z over x, and omega 02 is always dz1 and dz2 over z1 minus z2 squared.
Can I make a smaller mark? So I think I might have, last week I might have said that omega 01 is just y dx. There are actually two conventions here. So either you write it like this, like it's written right now, as y dx over x, or you can use another convention and write it as y dx. That means just exchanging x with its exponent. So sometimes you call you do not by x what is this x what is which is chosen here, or sometimes you take its logarithm and call that one x. In that case, omega 01 will be just y dx, right? So this is how I think I introduced it last week, but just keep this in mind and there will be no confusion. So you need to check omega 01 and then what is your x and how they are related. If there is dx over x, then it's the x is the large one, the exponential. And if not, then it's the logarithm. Okay, so is it clear? Is there any confusion regarding that still?
So
there
it's,
are just conventions. So just
yeah, it is more or less the same remark as I did before in my example when I took x to the x is equal to z squared, y is equal to z. For this example, it is I should take as omega 01 just y dx. But it is again the matter of
or instead you could write x pop to z squared, right?
Sorry.
Oh, I mean you could write another.
Yeah.
Instead of z squared, you could say that it's x pop z squared, right?
Yes.
And then use this y dx over x.
Yes. So maybe okay. And the recursion, what recursion gives? A recursion gives. So yes, this guy it lives in sigma. This guy. So it's a. Sorry, it's not an element. Yeah, it's okay. So
You
it's
always get things always in the CQ1 case.
yeah. So it's on one form on CP1. It's a two form on sigma squared, and the recursion produces omega gns of z1, z2, etc. zn, which are n form on sigma to the power n, which is again cp1 to the power n.
But note that I lives in the on the ith copy, so it's not like so that i's they are not belonging to this whole space. It's just that I lives on the ith copy of sigma.
Yeah. As I said at the very beginning, this z1 is a affine coordinate on sigma, the first copy of sigma, of the first copy of cp1. So z2 is the coordinate on the second copy of cp1, etc.
It might be helpful if you could write that I lives on ith copy. Just that.
Yeah. So the I is a coordinate on the ith copy of CP1. I yes, and okay. This is the initial data, and this is these differentials omega gns. So I think let's write the formula itself, and then we'll see, and then we'll see. Okay, how it works? So it works like follows. We have omega. Now I'm going to write down the recursion formula in the following way. For this notation, this z with index bracket n means that so z n means that it's a tuple of variables, tuple of coordinates. So it's a z1, etc. zn. Just set, yes. And so is equal to 1/2 sum. It's a big sum, and here is a big residue. Big residue. This residue will be in this simple zeros of this form dx over x. So these zeros of dx over x, this residue you should take in the zeros of dx over x. So in say w is equal to pi's, and this pi's zeros of dx over x. Then okay, again then integral from w to sigma of w, omega 0 2 of say z0 say t over omega 0 1 of sigma I of
Yeah, sorry, you meant sigma I also in the limit of the integral, right?
yes minus omega 0 1 over w, and here also should be sigma y of w. So who is okay, and then times something, but who is this sigma? Yes, and the bracket somewhere should be here. Who is sigma I? So again, this pi, again I should move this formula a bit. So it's not the end of the formula, but I want to define this sigma I. So Zn, this guy, pi is the zeros of this dx over x, and sigma. So we have these pi's are simple zeros of this dx over x. So it's in fact critical points of the function x, critical points of x of z, and so I want that these critical points of x of z are simple. What does it mean? That in the vicinity of this critical point, the
Of log x in this notation. Critical points of log x. I mean, when it's different.
yes, in this notation log x, yes. Yes, in this notation log x. Yes, so, of course. And so this function, okay, log x, maybe it was a mistake, but nevertheless. So this function log x in the vicinity of this simple critical point has two branches, and locally near this critical point there exists a holomorphic involution which change these branches of the function x. So, and this sigma is this holomorphic involution. For example, let me describe it in the example.
Yeah, it would have been a bit easier if we consider log x to be x.
Yes. So we have, okay, we had x of z is z to the power, it's okay, then log x, it's just log z minus z, and what is how it look like. So it's
maybe you could first explain the example where log x is z squared, just z squared.
Yes, it maybe, but okay, if x of z, so if log x of z is z squared, then we have simple critical point 0, and this involution with this involution will be just so this sigma of z is just equal to minus z. Yes, so we have two branches, and the involution just changed these two branches with the minus sign. In this case, what is the plot in this case? Okay, is it somehow clear or absolutely not clear?
So the condition on sigma is that x or log x of sigma of z is equal to log x of z.
Yes. So
it's an involution which preserves the value of.
Yes, definition that log x
simple zero of simple critical point.
Log x of that in the vicinity of simple critical point of log x of z. Да, ну то есть.
So what Mikhail suggested was to say that we cannot, in the vicinity of a simple critical point, we can always introduce a local coordinate w such that such that log x is equal to w
Yes,
squared.
yes. It's right. It's just a different way to think about it. Yes. Thank you. Yes. If you have a, yeah, I can repeat, but Petya already said that in the vicinity of near a simple critical point, you could choose a local coordinate, say w, such that this log x of z is equal to w squared, and then sigma is always this sigma of w is equal to minus w. In 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 real computations, I mean in computations, usually it's a bit harder, and you have to somehow solve these equations to understand who is this sigma, but nevertheless. So and the picture here like follows. Yeah, you have just z squared, and you have these two branches, and you switch these two branches.
Okay, yeah. Is it clear to everyone what is this sigma? Всем понятно, что такое sigma?
Is sigma defined on a neighborhood of the critical point?
Yes,
This strange word means just в окрестности. В смысле, мы же в окрестности, то есть мы все определяем. Вот эта сигма, она определена в окрестности критической точки.
We have its own sigma, and that's why we call it sigma I, as you can see in the formula down below. So we sum over all critical points, and I is the number of the critical point, and for each of the critical point, we have its own sigma I.
Yes. So this we define here sigma, and this sigma. So okay, Petya said, yeah. Да, в общем, эти сигмоиты, это вот эти, то, что называется иногда deck transformations или инволюции в окрестности каждой из этих n критических точек p-т.
Тут сейчас вопрос есть.
Why do we need logarithms in the future? It looks like we just write the equal.
Yeah, it's not important in that. In over there, it's not really important because we consider a critical point of log x. So the logarithm
the global sigma, the global sigma, not sigma.
the global sigma. So that depends on. So, for instance, in this example where log x is that squared, then you can say that it's a global sigma. But that depends on what is your x. So, for instance, if it has multiple critical points, that it's not possible. If it has just one critical point, then it's okay, you have a global sigma.
So could you repeat the question? Yeah.
Question was, can sigma be a global involution?
So if we have a one critical point, as that's what you said. Okay. So yes. If n capital is equal to 1, this n capital is equal to 1, then yes. Otherwise, no.
Actually, you have to at least exclude at least one point. So completely global even in that circle.
Okay. And then, so this...
One moment, there is another question.
That is incorrect.
I don't hear at all. Yes. Hello?
And down below, you have something which is one form in W. So at the moment, it's something not really well defined because the formula is not complete yet. The question was, is it just a number in the brackets?
No,
Because
no,
you have some differential in the numerator and some differential in the denominator, and so the answer is that the formula is not complete yet,
yes,
so it
yes.
doesn't make sense at this point.
By now it doesn't make sense. Yeah. So now we define all
I'm sorry,
this.
another question.
This is the sigma for the first exponential.
It's a little bit complicated. So there is the question regarding the Hurwitz example. So could you comment on what is the sigma there? In the
So yes, here we should compute something. Here we should compute something, and in fact, if we should use this definition, this definition, and therefore we have, say, log minus sigma of z is equal to log z minus z, and and we need to find this sigma of z, and so we will discuss it in details in on the seminar on practice, but the one way to deal with this is to find this sigma as a Taylor expansion. So we can, like, we again we leave at z is equal to 1, so we have to expand log z expand log z in z equal to 1, and we could find the first few terms of sigma of z, and this is this is okay. How to say, like, okay, this way is okay for us because of its it all what we need in fact in this recursive formula, which I will write, because of we take here just a residue of some huge guy in this z is equal to 1. Therefore it's okay for us just to find some few first coefficient in Taylor expansion of this sigma. Okay.
So closed formula for sigma in that case is not really viable, but for computing residue, you just need a few terms.
Yes. Okay, but I hope we'll discuss it in details on practice, maybe today or next week. We'll see. More questions?
Any more questions?
Okay, then I'm proceeding with this formula. So it's again this big sum in case of this example, n capital is equal to just 1, so we take residue only in one point, but in general case it's a big sum overall n, a big residue, and this is the first part, and the second part is gonna big brackets with omegas with smaller indices. So we compute here omega g n plus 1 through omegas with the smaller indices.
Smaller in some sense.
Yeah. Smaller, in fact, in okay, we'll see. W sigma I of W I again. Okay. Z n. plus some prime. G1 plus G2 is equal to G. E1 E is equal to N. So what's written here? Here I wrote omega G minus 1 N plus 2 of W, sigma of W and Z and brackets. It's okay, just some omega, which if I'm lucky, I computed on the previous steps of this recursion, plus some omega, so some overall partitions, so overall G1 and G2, which are G1 plus G2 is equal to G, this G, and E and I and J is a partition of one of the set from 1 to n into two subsets. So I and J are two subsets of indices from 1 to n. Omega G1 modulo I plus 1 of WZI times omega G2 J plus 1 sigma I of W. Okay. Okay, maybe it's better if I just rewrite it a bit. So here plus and here plus and here times omega G2 plus 1 sigma I of W Z J. So this bracket I close here, and this bracket I also close here.
So, maybe let's turn to the audience. So, going back to your question. So, what is this object now?
Maybe a bit. So few seconds more. So what is just written here? So again, this z with index I capital means, so for example, means that it's a tuple of variables, tuple of coordinates z e1 etc z e say k, where I is equal to I1 etc ik, and again I and j together gives the set 1 from 1 to n, and what else here, this g1 g2 is okay, and the sigma I again, those sigma I, and also this omega, these omegas with which are computed on the previous steps of the recursion. And what this prime means, this prime means that we exclude from this sum all the summands where omega 01 could be. So it is forbidden to have here omega 01. So it's, maybe I could erase, but some prime means that there are no summands with omega 01. So it's not possible to have G1, for example, is equal to 0 and G2 is equal to G, and in the same time I capital is empty and J capital is equal to from 1 to n. So it's forbidden. So there are no summons here. There are no summons omega 1, 0, 1. And I think formally that's all. So I define all the symbols here. So this is the formula. So again, this residue of all these three lines.
Before you explain how the residue works and what are the arguments, I wanted to ask the audience to think about that. Is it okay?
Yeah.
So going back to your question. So what is this object now in the bracket?
It's form of DW. And
So yes, here maybe I can just write down. So this, say, in fact, we don't hear you very well. So maybe Petty, you can repeat what.
I can also maybe increase the sensitivity of the microphone. Yeah.
So now I hear you very, very well, but then
So
yeah.
is it better? Is it better like this?
Yes.
There is t under the integral sign, and what is t?
T is the variable over which we integrate in this small integral.
Yeah. So let me maybe okay.
Maybe let's put dot instead of t.
Maybe let's put dot instead of t. So I meant there that this integral sigma I of w, it just written like dz0 dt over d dot, yes, z0 minus t squared, and this integral over t.
We take the integral over t. So z0 remains. We are left with dz0. So just once again, so could you please all think about this? So what is this sort of object which we have under the residue? So you see that we have this ratio first, where in the numerator we have some differential. Then in the denominator we also have some differential.
So let me write it down. Yes. So in fact, this
what object is that?
this is one form. Yes. Do we agree that this is one form?
On which copy of sigma does this live? So on the left-hand side, you see we have this omega gn plus 1, which is defined on this sigma to the power n plus 1. And we have z0 and so on, zn. Each of them, zi, lives on the ith copy of sigma. And let's compare it to what we have on the right-hand side. I mean, on the right-hand side, we should have the same thing, right? It's the same object by definition here. So what are the variables entering the right-hand side, and how do they enter the right-hand side? Sorry?
N plus 2.
Yeah, so we have, let's see, we have this n plus, in fact, on the right-hand side, under the residue, we have n plus 2 variables, w and z0 and so on, zn, right? So n plus 2 variables, but then we take the residue in w, and then w disappears. But let's check what sort of the structure we have under the brackets. So we have some n-point differentials, right? Or n plus 1 and plus 2 point differentials. What remains after we take into account the denominator and so on? So let's see.
So again, here we have one form in z0 variable, yeah, in the numerator, and what we have here in denominator.
What do we have in the denominator?
We have the one form given by the integral and n plus 2 form.
Yes, but in the denominator,
In this small denominator,
we have one form in w, right? In the variable w. Okay, and not in the in the brackets in the.
So here, yeah.
And then in the small brackets, what do we have there?
So this guy.
But you see, those guys, they both of the terms, they depend on W 2 times there. You see?
Yeah.
So it appears as the first argument and the second argument in the first term, and it appears in both of the factors in the second term.
So let me write it like this. So it's an n plus 2 form in the variables w, w, and then z1, etc., zn. Yes? Okay? So on sigma to the n plus 2, yes?
But it's not the same sigma plus 2.
Yes. So it's not the same sigma n plus 2. It's those n plus 2 copies of sigma which have this ww coordinate on the first two copies, and then z1, etc., zn.
So the first copies are one and the same, actually.
Yeah.
And so what do we see? This guy in the small brackets, it depends. It has two instances of dw, you see? And then in the denominator, what do we have? In the denominator, we have one dw, right? So in the end, what is this guy in the large square brackets?
Where is the denominator? Second.
In the denominator, I mean this one.
The
0.01 is
this Petya means this denominator.
It has dw. It's something times some function of w times dw, right? Okay. So we have dw here in the denominator, and we have dw 2 times here in the brackets.
So where do the brackets begin and where do they end?
So we have this. Oops. Okay. Let me write it like this. We have this blue bracket with these small blue brackets and these big green brackets. Okay. So in blue brackets we have n plus 2 form in variables ww, z1, etc., zn. And in this before this prefactor is one form in z0 times this prefactor. I mean one form in z0 over one form in w. So in the end we have something like this. We have some function times so dz0 over dw, some functions, yes, something here. So very roughly speaking, yeah. And then times dw, dz1, etc., dzn times some functions. Does it make sense, this? So it's very roughly speaking what's written here.
If we say the differentials are not skew symmetric, because if they were skew symmetric, then
they're not skew symmetric.
No. They are absolutely independent. It's this dw. It's a differential on. It's a one form on its own copy of sigma.
So actually, our omegas, they're symmetric, they're.
Yeah. So we'll see it somehow, but yeah.
So these are symmetric multi-differentials defined on.
But what we wanted to say that after so we have this cancellation of this d omega dw, sorry, and dw in denominator and numerator, and then we take a residue in this point. Say if we have one point p1, then we obtain exactly so this d omega dw, sorry, kills by a residue, by taking a residue, taking a residue, and so we obtain the same object as on the left hand side, this n+1 form on n+1 copies of sigma with coordinates z0, z1, etc., zn.
So you see, here we use of course, the definition of residue of a one form, right?
Yes.
When we a number out of a one form. So that's why the remaining dw cancels by taking the residue. Is it clear?
So there are no skew products.
No skew
No.
products. Everything is symmetric.
Yes. So no questions because of nothing is understandable or something is okay.
Of course, I mean, this huge formula is quite hard to understand at a glance. So we will compute examples.
Yeah.
And then we'll see how to work.
Okay, maybe let's proceed then. So this is the
Sorry, there is a question.
We also need to check that the integral is well defined, right?
You mean the integral above? In the numerator, right?
Yes. So
Yes, but the point is that it's only we're interested in it locally because we're only interested in taking a residue at some point pi. So we assume that W lives in a small vicinity of pi, and then with our conditions on omega 0,2, the integral is well defined actually. So let's see. That requires some discussion. So let's maybe see why the integral is well defined.
Yeah. So yes. It's okay. Let's. So it's written here. Yes, we have this integral over W from W to sigma I of W dz0 dt over z0 minus t squared. So what is it?
Is taken over t. Okay.
Yes.
Here remains. So maybe you can already put it out of the integral.
Yeah. Yeah. Great. So dt, this integral. Yeah. So what is it? Yes. Let's compute.
So can someone say what is the answer?
So it's say like you just what is the. То есть, в общем, мы хотим просто вопрос посчитать интеграл. Да.
Давайте подождем, пока кто-нибудь посчитает.
Да.
So let's wait. And we will see that it does not depend on the contour, right? So it does not depend on the path from W to sigma I of W. And that's why it's well defined.
Here, sigma W is just minus W.
No, in fact.
I mean, if we introduce this W as a local coordinate at this critical point, such that log x is equal to W squared plus constant, then yes.
Then yes.
For the moment, let's not assume that.
Yeah. Let's not assume that.
Okay, you can introduce this assumption at the end, right? I mean, for this computation, it doesn't matter. You can write it down in terms of sigma, and at the very end, you can, if you want, introduce this assumption.
So okay, it's not hard to integrate just function 1 over z0 minus t squared, yes? So what we'll get?
It will be dz over z minus t, z0 minus t.
So so something like this, yes?
Yes. Without 2.
Without 2. Just this.
Yes.
Well, what does it mean? Because t is a variable of integration, it's not a free variable.
Yeah, you need then substitute the limits.
Brackets.
And what to do with minuses, pluses? What should I write here?
Seems to be correct this way.
Okay, and so
Well, I think there's an additional minus sign.
But you get the minus sign from the power, and then minus sign from minus t.
Okay, I see.
okay.
Let's join together those fractions.
Yes, so everybody agreed, yes?
Does everyone agree with what's written there?
Yes.
Yeah, okay. So we have something like this, dz0, say what in the numerator?
It should be sigma I of w minus w.
Oops, over, okay, yeah.
Well, z0.
And maybe at this point, let's also additionally write what happens when W is a local coordinate such that log x is equal to W squared plus constant. So maybe you can write a remark. So if log x is equal to W squared plus a constant.
So if W is this coordinate, yeah. If W is
if log x is equal to W squared plus c.
Yes.
So this is always, you can always choose if our point Pi is a simple critical point of log x, then you can always choose W as local coordinates such that this holds, right? Then sigma I becomes just minus, in this local coordinate, it becomes just the multiplication with -1. And our integral turns into what?
So minus 2W, yes, over
z0 squared minus w squared.
yeah, dz0, yes? And yeah, so you see that, yeah.
And you see that it does not depend on the path. If everything happens if everything happens in a small vicinity of pi, of our I point, then of course this integral is well defined, as it does not depend on the particular path you take from W to sigma of W, like you see from that, right?
Okay. So it depends only on W. Yeah.
Are there any other questions regarding the general formula? Maybe you can show the whole formula again.
Yeah. So
maybe you can draw this picture with mnemonic.
Maybe what I wanted to say is what I said that something strange. Okay, the recursion runs on not on G or on N separately, but on 2G minus 2 plus N. So the recursion, let me write it somewhere. I don't know where. Okay, the recursion goes on 2G minus 2 plus N. So we have here, say...
There is some space right before under the... Okay.
Okay, or here. So we have, I don't know. Oops. We have 2G minus 2 plus N plus 1 here. So it's 2G minus 1 plus N. And this is 2G minus 2 plus minus 2 plus N plus 2. So I should write somewhere 2G minus 2 plus N. So the recursion goes on 2G minus 2 plus N. So in the left hand side, 2G minus 2 plus N is equal to 2G minus 1 plus N. In this omega, 2G minus 2 plus N is equal to 2G minus 2 minus 2 plus N plus 2. So is equal to 2G minus 4 plus N, I think. So it's smaller. It's smaller.
It's the minus 2.
No, it should be minus.
Sorry. 2G minus 1, so 2G minus 2. Yeah.
That should be like that.
2G minus 2 plus N is smaller than 2G minus 1 plus N. And
there by 1, right?
Yeah. And smaller by 1. Yeah. And here we have, G 2G1 minus 2 plus 2G2 minus 2 plus what? Plus N plus 2, yes? Which is, yes, which is again 2G minus 2 plus N. It's again smaller by 1 than in the left hand side. So here we have 2G minus 2 plus N, and here we have 2G minus 1 plus N, 2G minus 2 plus N, 2G minus 2 plus N. So this recursion goes on this, say, earlier characteristic of something. So if we start from omega 01 and omega 02, we know omega 01 and omega 02.
But just on remark, so it's important that we did not allow the 0-1 terms, because let's look at the formula. Suppose that we had a 0-1 term somewhere. So suppose that this guy is 0-1. What will this guy be then? So if the first factor here is 0-1, meaning that G1 is equal to 0 and I is empty. this will be yes, G
N
n plus 1,
Sorry.
which is the same as here. And then it will not be a recursive formula then, right? Is it clear? So this works only because we have this prime. So it works as a recursion
Yes.
on these 2G minus 2 plus n, only because we did not allow the 0, 1 terms. Okay?
There are also more subtle reasons why we exclude here this omega 0, 1 term, but this is also true. And so we're starting from omega 0, 1 and omega, omega 0, 2. We obtain, for example, omega 0, 3, which is, for example, yes. So we have there, which is who is omega 0, 3. Yes, we have this 1/2, some residue, doesn't matter by now. Some this prefactor, which is something, and in this big green, no, in this big blue brackets, yes. So in this big blue brackets, what we have? We have for omega 0, 3. So if omega 0, 3, so we have G is equal to 0 and N is equal to 2. G 0, N is equal to 2. And we have here, here we have, you see, omega minus 1, it's 0. So we have 0 plus some overall partitions of G, which is 0. So we have no these partitions of this kind. So we have only partitions of indices 1, 2 into 2 subsets, such that 0, 1 excluded. So we have something like this, I think. Omega. So we have partitions like 1, 2. So I is equal to 1, J is equal to 2. And
The other way around.
sorry.
And the other way around. So.
And vice versa, yeah. And I is equal to 2, J is equal to 1.
But can we have I empty and J is equal to 1 too? For instance, can we have it? Can we have I to be empty and J to be everything?
Omega.
No, because of the prime, precisely. Yes.
So yes, and we have here omega 0, 1, omega, sorry, what 0, 2. I should write omega 0, 3, Z0, Z1, Z2, yes. And here I write omega 0, 2, W, Z1 times omega 0, 2, W, Z2. Oh, sorry.
Sigma down.
Sigma of W, Z2 plus omega 0, 2, W, Z2 times omega 0, 2, sigma of W, Z1. Something like this. Yes, and then if we have, say, n is equal to 1, sum from 1 to 1, then sigma, we have only one sigma. For example, yeah.
Here you can write, here you haven't yet substituted anything specific to this example, so you can just keep
Yes, but then yes.
I think we need to break.
Yeah. Okay, so we had today we had this huge formula and
Try to compute some specific examples.
Yeah, some specific examples. Yeah. And the next time, I think we'll continue to discuss this formula and some properties of these omega gens, etc., etc. Okay.